Hello, this is Luca and
ZJ.
from NYU Shanghai, and in this video we will present our project about human weight recognition for the spring 2017 machine learning class.
In 2014, Business Insider wrote that roughly 1.8 billion photos were uploaded to social media platforms including Facebook, Instagram, Snapchat, and so on. The number has been constantly increasing ever since, and it is very likely that it will keep increasing in the foreseeable future. We all know that tech companies like Facebook and Instagram exploiting the huge accumulation of photos on their platforms use face recognition algorithms to label users in the picture that they upload. However, one's face doesn't really tell much about the person. Instead, physical characteristics about a user can provide much more information that can be employed in order to suggest products that better suit the user's needs. This project aims at classifying users according to three categories of body weights: underweight, normal weight, and overweight range. The relevance of the project stems from the fact that having an estimate of people's body weight can help companies at differentiating their advertising campaign according to their audience. For instance, if an airline company knows that a customer has a relatively bigger body size, it can suggest her to purchase a ticket for a seat with more room. In the project, our goal is to train a convolutional neural network that is able to recognize to which of these categories the person in a picture belongs to. Now let's take a look at the dataset and its configuration.
Currently, there is no existing dataset of pictures that describe the three different classes of body weight of our interest, so we created ourselves. In total, we collected 3,600 pictures, 1,200 pictures for each class, from Google Image and Instagram. In every class, there is an equal number of male and female people. The pictures were labeled according to the searching parameters on Instagram and Google Image. For example, on Instagram, we would look for the hashtag skinny, and the corresponding images would be put under the skinny class. This is to say that we did not absolutely classify people according to their weights and use pre-existing labels.
We pre-processed our data using Keras image data generator. We made two generator functions, one for our trained data and another for our validation data. The trained data and validation data was split into two folders according to the Pareto principle, which states that for many events, 80% of the effects come from 20% of the causes. Each folder contains three folders according to the three classes of our study. The method flow from directory automatically generates the batches and recognizes the number of classes according to the number of folders. We then resize our images to 150 by 150 pixel size. This size was chosen after a long parameter tuning, as it turned out to be a good compromise between computing time and accuracy.
Now that the structure of the dataset is clear, we can move to the description of the architecture of the model. For this project, we used the VGG16 architecture, pre-trained on the ImageNet dataset. VGG16 is known for its deep convolutional neural network that contains 16 layers. In general, its performance in object classification is remarkable. The architecture of the VGG16 consists of 5 convolutional blocks with an increasing number of filters: 64 for the first block, 128 for the second one, 256 the third one, and 512 for the fourth one and the last one. It then follows a fully connected classifier.
In this model, we only instantiated the convolutional part of the model, everything up to the fully connected layers. We then recorded the output of the convolutional blocks in two NumPy arrays. In the end, we trained a small fully connected model on top of the stored features. The reason why we are storing the features offline rather than adding our fully connected model directly on top of a frozen convolutional base and running the whole thing is computational efficiency. Running VGG16 is expensive, especially because we are working on CPU and we want to do it only once.
In this model, we set the batch size as 20, and we chose 10 for the number of epochs. This is because, based on our experience, overfitting seems to take place around 10 epochs. After 10 epochs, even though the accuracy for the training dataset continues to increase, there is not much improvement on the validation accuracy. Therefore, we set the epoch at 10. In terms of dropout value for the fully connected layer, there is not much difference among the results when the dropout value is between 0.2 and 0.5. Here, we set the dropout value as 0.5 to prevent overfitting. The results that we obtained for the three classes weight classifier with these parameters are satisfactory. With only 3,600 images, we were able to reach a validation accuracy between 60% and 65%.
Now let's take a look at the demo. The model and its weight were saved in human weight recognition.py file, and it has already been trained. Now we will use a separate file called prediction.py to make predictions. We are running the code in Spider. As you can see, the result returned by Python is an array of several 1x3 arrays. There is one element in every array that is close to 1, and the index of that largest element corresponds to its label. Here, the labels are 0 corresponding to overweight, 1 corresponding to normal weight, and 2 corresponding to underweight. The following are the prediction results of pictures that the model has never seen. The first picture is Luca, and he is recognized by the machine as normal weight. The second picture is a random result of Google Images when searching with the keyword overweight, and it's classified correctly, and so on and so forth. The last picture is a random result of Google Images of the keyword skinny, and its prediction result is underweight. During the training process, we were also able to confirm the hypothesis that we made during the data collection. The neural network struggles to learn features that differentiate normal weight people from underweight people. As a matter of fact, if we reformulate the problem to a binary classification problem and try it out with all the possible combinations, we got the following results. The validation accuracy in the binary classification problem with the classes underweight and overweight results in a validation accuracy of almost 90%. The validation accuracy in the binary classification problem with the classes normal weight and overweight results in a validation accuracy of around 79% to 81%. And the validation accuracy in the binary classification problem with the classes underweight and normal weight results in a validation accuracy of only 63% to 67%.
As we can see from the results, even though our dataset for the three classes is extremely small, it can still tell the difference between people of different body sizes. However, when it comes to normal weight people, the similarities between them and both overweight people and underweight people kind of confuse our CNN. Even though we acknowledge that 65% is far from a perfect model, it still shows that this kind of problem can be addressed in terms of convolutional neural networks, and leave hopes that with a larger dataset, the accuracy might actually increase by a lot. So, this is the end of our project. Thank you for watching, and if you have any suggestion or remarks, please leave a comment.